Good afternoon. I hope you're more perked up now you've had your favorite cookie and a cup of tea or coffee. Okay, I'm just going to put this down. All right, so this afternoon's lecture is going to be on the fundamentals of the analysis of neuronal oscillations. Okay, so when you're looking at MEG, EEG data, there are the temporal aspects of the data and also the spatial aspects of the data. So this morning you focused on looking at event-related fields. And this afternoon, we're going to take a closer look at spectral decomposition. Just a heads up, later this week, you guys will also have a lecture that focuses a bit more on the spatial aspects. Okay, so the brain signals, they contain oscillatory activity at multiple frequencies. And here what you see on the top figure is the very first MEG experiment that was done back in 1972 by Cohen. And it is a replication of the earlier EEG study done by Hans Berger back in 1920. And what this experiment showed was that when the subject's eyes are closed, there is a much higher amplitude in the oscillation than when the subject's eyes are open. And this is a very robust effect. Now, a more recent study also showing changes in the brain activity is a study that was done here at the Donders back in 2006 by Hohenbohm and colleagues. And this study showed that when subjects looked at concentric rings, and the concentric rings were moving inwards, what they saw was an increase in oscillations between 60 to 80 hertz, and a decrease in the oscillatory power around 20 hertz. The goal of today's lecture is for you to be able to understand spectral analysis and also to be able to interpret this figure here on the right. Okay, so the outline of the lecture, we're going to start off talking about what spectral analysis is, and then we're going to talk about the issues about finite and discrete sampling and how they impact spectral analysis. Namely, it leads to the issue of spectral leakage and how we can control leakage with tapering. And in the last part of the lecture, we'll devote some time to talking about time frequency analysis. Okay, so just to make sure everybody is on the same page, we're going to do a quick background on what oscillations are. So here we have an oscillation. An oscillation is nothing more than a line that wiggles back and forth relative to a fixed point, so just the line in the middle. And there are three features about the oscillations that you want to keep in mind. Now the first one is the period, and that's the distance between one peak of the oscillation and the next peak that follows. If you take 1 divided by the period, what you get is frequency. So that's the number of cycles per second that your line is wiggling at. Now you can see that the wiggle is not continuous. It's not a stationary wiggle over time. And you can see that it fluctuates. Now what you can do to capture this is draw a line over the oscillation, and this is the envelope. And if you take the distance from the peak of the envelope to the 0 point, what you get is the amplitude. So that tells you how strong the oscillation is wiggling at. Okay, the third property then is phase. And phase refers to the certain point in the cycle of the oscillation relative to a fixed point. And here I've tried to demonstrate phase using these jagged lines. So say we take this peak, so the first point here, as 0 degrees. And as you go halfway down the cycle, you're at about 180 degrees. And when you go back up to the peak, you're back at 360 and the cycle starts again. So in this way, phase quantifies where you are in the cycle of the oscillation, and you can express it in terms of degrees, also known as a radian angle. Okay, so just to sum it up, 3 features of an oscillation: period, that gives you the frequency, the amplitude, and the phase. Okay, now, so when we're doing spectral analysis, what we're actually doing is we're taking our signal from the time domain and we're decomposing it into its oscillatory components in the frequency domain. And this is also referred to as Fourier analysis. And these basic oscillatory components are also referred to as basis functions, and they are basically the cosines and sines. And so what we show here on the top signal is a cosine, and the bottom is a sine, and these are just 90 degrees shifted relative to each other. Okay, so let's take a closer look at the concept of what spectral decomposition is. So here we have a signal, and it's composed of many individual frequencies, shown here in red. This is extremely difficult to see, so we're going to spread them out. And what you can see is that our signal here in blue actually consists of 3 different frequencies. And each of these frequencies has their own amplitude and phase values. So the frequency on the top has the oscillation on the top has the highest frequency, but only an intermediate amplitude compared to the other 2 signals. Now, if you had a very complex signal and you had to show what the individual frequencies were in the signal, you would spend a lot of time drawing many wiggly lines, and that's not very efficient. So we tend to represent the frequencies in our signal by using a power spectrum, and that's the figure here on the right. So on the x-axis, what you have is frequency, and on the y-axis, what you have is power. And you can see quickly that we have signals at about 4, 6, and 9 hertz, and they each have their own respective power. And I should mention that power is simply the squared amplitude of the frequency. Okay. So just to quickly recap, spectral analysis is taking your signal from the time domain and putting it into the frequency domain and breaking it down into its constituent oscillatory components. And doing this, you're expressing your signal as a function of frequency instead of time, but keeping in mind that these 2 are just mathematical equivalents of each other. Now, another way to think about spectral analysis is using linear regression, in the sense that we want to explain the signal using linear regression with oscillatory basis functions. So in linear regression, what we want to do is we want to fit a set of beta weights to our design matrix to explain the optimally explain the amount of variance that we have in our signal. In our case, our design matrix consists of various basis functions, like the ones here. And we want to see how well each of these basis functions fit into our signal y. Now each of the weightings, so each of the beta weights for the basis functions for a given frequency, so say you have a 10 hertz signal, then you have 10 cycles of a cosine and 10 cycles of a sine. The beta weights together can map onto an amplitude and phase estimate. And let's take a look at how this works. So say we take these 2 basis functions and we map them onto a 2D plane. On the x-axis, what you have is the beta weight for the cosine, and on the y-axis, you have the beta weight for the sine. When you take these 2 values together and plot a coordinate onto the 2D plane, and you draw an arrow from the origin, the arrow represents the amplitude for the frequency, and the angle from the arrow to the x-axis tells you what phase that frequency has. Okay. Now it's important to keep in mind that your basis functions should be orthogonal. And the reason for this is so that each basis function can explain a unique amount of variance in your signal. But if you don't remember that, the important part to remember is that the orthogonality restriction applies 2 consequences when you're doing spectral analysis. The first one is that the frequencies that you use to estimate your signal are not arbitrarily chosen. You can't just pick the ones you like. The frequencies you can choose have to fit an integer number of cycles into your data. And the second consequence is that if your data is consisting of n points, you can only use n basis functions. Okay, so let's take a look at each of these consequences in a bit more detail. So consequence number 1, you can't randomly pick your frequencies. These frequencies that you can use have to fit an integer number of times into your data window. And the frequencies that you can estimate is also referred to as the frequency resolution, and that's determined by the length of your data segment. It's also referred to as the relay frequency. And what you do is you take 1 divided by the time in terms of seconds of your data window, and then that gives you the frequency resolution that you can have to estimate your data. So if I have a time window of 1 second and I take 1 divided by 1, my primary school teacher tells me that I can estimate frequencies at the interval of 1 hertz. So I can do 1, 2, 3, 4, 5, so on and so forth. I can't do 1.5, 1.2, 10.9. That's not happening. Now, if I have a time window of 0.2 seconds, does somebody want to tell me what frequency resolution I can get? No, Yamatais, you can't answer. I'm sorry. Ricardo? Yes, exactly. So you can estimate in 5 Hz intervals. So this says that your time window constricts the frequencies that you can estimate. Okay, so the second consequence is that given that you have an endpoint signal, you can only use n basis functions. And since each frequency that you want to estimate has to be represented by 2 basis functions, that means that you can only actually estimate at n divided by 2 frequencies. And here n refers to the highest frequency. The highest frequency that you can resolve depends on your sampling frequency. And so if you collect your data at a certain frequency, it has to be half of that. And this is also referred to as the Nyquist frequency. So if you have sampling data at 1,000 Hz and you have a time window of 1 second, then you can sample at 1 Hz intervals, so 1 Hz, 2 Hz, and the highest frequency that you can estimate is at 500 Hz. Similarly, if you have a sampling frequency of 400 Hz and a time window of 0.25 seconds, then you can sample in 4 Hz, 8 Hz, so on and so forth, and the highest frequency that you can resolve is 200. Okay. So we've talked about spectral analysis is bringing your signal from the time domain into the frequency domain using basis oscillatory functions. And in doing so, you're expressing your signal as a function of frequency instead of time. We also discussed that you can consider spectral analysis as linear regression using oscillatory basis functions to say how well these basis functions fit your signal. And that we also talked about each oscillatory component has an amplitude and a phase value. Now with these things in mind, another thing to keep in mind when you're doing spectral analysis is that there is the discrete and finite nature of sampling of your data puts certain constraints on your frequency axis when you're doing spectral analysis. Okay, so when we're doing spectral analysis, what we aim to do is estimate the true oscillations in your data, granted that you don't actually know what frequency your subject is oscillating at. And the thing is, we only have a limited time window available from the entire point at which the signal is whirling at. So that means that you have a limited time available for doing your Fourier transform. And in essence, that's like looking at your brain activity through a time-restricting window. And when that happens, it's the same as implicitly applying a boxcar taper to your signal. And I'll talk about boxcars in a bit more in the next slide. So finite sampling means that you can only get a restricted time window of your data. And the discrete nature of sampling means that within that finite amount of time that you have, what you get is coarser segments. So as an analogy to this is estimating your true oscillations is like trying to reconstruct this entire photograph of the castle. But finite sampling means that you can only reconstruct it from the part of the image that's inside the box. And discrete sampling says that, well, the part inside the box is actually cut up into smaller segments. And that's actually quite difficult then. So this brings us to spectral leakage. Finite and discrete sampling leads to the issue of spectral leakage. And what is spectral leakage? Well, spectral leakage is when the true oscillations in your data at frequencies not sampled with the Fourier transform will spread their energy to the sampled frequencies. And this is same as implicitly applying a boxcar taper. And the thing is, each taper has its own specific leakage profile. So here we have a boxcar taper. The part of the signal So the boxcar taper allows part of the signal to go through, but the edges of the boxcar taper then tapers off the rest of the signal and brings it down to 0. And that's why you only have a small section of your data that is allowed through the Fourier transform. Importantly, this boxcar has a specific leakage profile. And this leakage profile tells you how much energy from frequencies that you're not estimating will have their energy spread to the frequency of interest. So on the x-axis here, we have frequencies as the distance from the frequency of interest. And on the y-axis, what you see is the amount of energy spread from frequencies that are not being estimated but are next to their frequency of interest. So maybe it's better to point. So say that you're interested in estimating 10 hertz. So then if you step this way, this is 11, 12, 13, 14 hertz. And if you step backwards, then it's 9 hertz, 8 hertz, 7 hertz, so on and so forth. And what we have here is in the main lobe, this is your frequency of estimate. This is the most amount of energy that is contributing. But the side lobes tells you that energy from other nearby frequencies also contribute to your frequency of interest. So in this case, if you're estimating at 10 hertz, then frequencies at 11, 12, and 13 do not contribute energy because there's a trough. But frequencies at 10.5, 11.5, 12.5, and so on and so forth will contribute energy to your frequency of interest. Okay, so let's take a look at a piece of data. So here we have a signal that fits a integer number of times into the observed time frame. But what you could also have with your data is signals that do not fit into the observed time frame. So in this case, you've got a 2.5 and a 3.5 hertz signal. Now, Fourier analysis assumes that your signal is periodic. So even though we can only look at a small chunk of data, we expect the signal to be repeating itself over and over again. And to sort of simulate this, what we can do is mirror the signals on each side, like this. What you see for the top signal is that from one time frame to the next, there's a very smooth transition, so there's no break. But when you look at the second and the third signals, what you see is a very sharp transition for the second one, and there's a very obvious jump here on the third signal. And it is in this case, when you have a sharp transition, that there is spectral leakage, and that you need many other frequencies to explain the frequency in here at 3.5 hertz. Okay. So how do we deal with spectral leakage? Well, what we can do is apply more tapers. And so here we have our signal, and what we're going to do is we're going to apply a taper to it. And in essence, it brings down the signal at the edges, so that, and it does this for the same for the other two frequencies, so that now if we show it as a periodic thing, repeating over and over again, you can see there is now a smooth transition. There's no more jump from one time frame to the next. And in this way, we're controlling the spectral leakage. Okay, so let's take a look at another example of tapering. So here we have a Hanning window, and we're going to apply this to a 40 hertz oscillation. And as you can see, it's tapered down on the edges, and so that when we repeat it, this creates a smooth transition. So we've controlled the amount of leakage that's going on. So going back. So true oscillations in your data at frequencies not sampled with your Fourier transform will spread their energies to the sampled frequencies. And this is implicitly the same as applying a boxcar taper, and that each type of taper has a specific leakage profile. Now we said that if you want to control leakage, what you need to do is apply a taper on top of your signal. So then what you need to keep in mind is that different tapers have different spectral leakage profiles. So here we have a Gaussian window, and it has a different type of spectral leakage profile. So you can see that the main lobe is very wide, but the side lobes are much smaller. So in this case, frequencies that are near your frequency being estimated contribute less energy to the main lobe than it did for the previous taper. And now if we look at the Hanning window, you can see that again there's a different spectral leakage profile. This time the main lobe is more narrow, but there is a decrease in the amount of energy contributed as you go further away from the frequency being estimated. Okay, so far we've seen that you can apply one taper to your data to control leakage. But actually in spectral analysis, what you can do is also apply multiple tapers and benefit of the combined effects of these tapers. And in doing so, what you're doing is actually smoothing your estimates in the frequency domain. And instead of smoothing, we can also say that this is controlling the leakage. So let's take a look at how that works. So on the top here in blue, we have a simulated signal for 2 seconds. And we're going to bandpass it so that we get the signal to come out at 60 to 90 hertz. And we've used this only with a Henning window, so this produced quite a spiky profile in the power spectrum. And now what we're going to do is, instead of applying one taper, we're going to apply more tapers. So going from left to right, you can see an increase in the number of tapers applied, and you can see that as you apply more tapers, you get a more smooth representation. So how does this work? Well, here again we have our 40 Hz signal that's been tapered by one taper. But now what we're going to do is we're going to take a look at the effects of what happens when we applied multiple tapers. And here what you see in blue, green, and red are the first 3 tapers that are part of the Slepian sequence. The one in blue is just the one we've seen before. And then the green one has been inverted twice, and the red one has been inverted 3 times in comparison to the first taper. So that's the one in blue. And the effects of these tapers individually on our data is that the first taper tapers the signal down at the edges. The second one inverts it in the middle. It suppresses it in the middle and inverts it twice. And the third one brings the signal down at thirds along the signal and inverts it 3 times. The effects of this inversion and applying multiple tapers are, I think, most clear when we look at it in the frequency domain. So here, what we showed is that the first taper gives you a peak at 40 Hz. The second taper gives you a peak on either side, so at 39, 41. And the third taper gives you less of a peak and more of a broader bandwidth in terms of what it does to the signal. Now what you want to do with multi-tapering is that you take your signal and you apply the taper to the signal independently 3 times, do the Fourier transform, and then you combine the transformed signals back together, and what you get is a smooth representation of your data. And that's exactly what we showed earlier. Now the important thing is that when you're doing multi-tapering, you want to apply it for every trial. Between trials, there's a lot of variance. So it means that for one trial, you might have this kind of spiky profile on the top, but for the next trial, the spikes will be in a different kind of manner. And by applying multi-tapers to each trial, you can reduce the amount of variance and in turn increase the amount of sensitivity you get in order to detect the effects that you have in your data. And the increased sensitivity is good, for example, if you want to do statistics as well. Okay, so multi-tapers are useful for getting reliable estimates with high-frequency components. But for low-frequency components, we're usually pretty okay with just using one taper, and that is usually the Henning taper. So how do we implement frequency analysis in field trip? Well, we need the function FD-FREC analysis. And as you guys learned, we begin by starting defining an empty configuration. And the method, importantly, the method you want to specify is MTM-FFT. And a couple other parameters that you need to specify is which frequencies you actually want to do your estimates on. So you go, in this case, the low ones, we want to go from 1 to 30. And then we have to just specify that we just want one taper, and we're going to use the Henning taper. Then in the case of high frequencies, what changes here now is that you specify that you want to use multi-tapers, and here we give the string input of DPSS, and this just refers to the Slepian sequence. But the other thing you have to specify is also the amount of smoothing that you want to do. So that's the CFG.topsmo-fric field. And here you say, I want to smooth my signal by 8 Hz. Keep in mind that this is a plus or minus 8, so that means if you're going to estimate your frequencies at 30 Hz, what you're doing is actually going from 22 to 38. So it's a plus and minus value. Okay. So, sub-summary. We've talked about spectral analysis. You're taking your signal from the time domain and you're bringing it into the frequency domain, and you're breaking it down into its constituent components in terms of basis functions. And we also made the assumption that when we're doing spectral analysis, that your signal doesn't change over time. It has the same amplitude the entire way through. So that's the point about stationary power. Now, we also talked about tapers. When you're doing with the Fourier analysis, because of finite and discrete sampling, you're implicitly applying a boxcar taper. And this boxcar taper has a unique spectral leakage profile. And in order to control the spectral leakage, we talked about applying different types of tapers to control this leakage, such as the Hanning taper or the Gaussian taper. We also talked about the advantage of using multiple tapers when we want to estimate higher frequencies. Okay, so now we're going to move on to time frequency analysis. The fun part, I think. So typically, we think that brain signals are not stationary. We don't actually expect the amplitude to be consistent all the way through the time period that we're observing. So what we have to do is to do a time frequency analysis. And to do this, what you're doing is you take your signal and you chop it up into individual bits, and for each individual window that you've chopped it up into, you're going to apply a spectral analysis. And so this means that everything we've talked about in the first half of this lecture still applies. The whole thing about tapering, about spectral leakage, about what frequency resolution you can use, all these things still apply. And if you want to do a time frequency analysis, you now have to change the method being specified to FT-FREC analysis. So instead of MTM-FFT, you now need to specify MTM-convol. Okay, so now we're going to take a closer look at the details of doing a time frequency analysis. So here we have, again, a simulated signal. And as you can see, the amplitude is largest roughly in the middle, and then it goes back down again. Okay. So previously, what we did was we expressed power in terms of in a power spectrum. So what we had was frequency on the bottom and power on the y-axis. And power is expressed just in terms of a line. Well, peaks, sorry. But now what we're going to do is we're actually going to express power in terms of color. So the more red it is, the higher the power. And we're going to show how power changes as a function of frequency on the y-axis and as a function of time, which is on the x-axis. So we have our signal, and what we're going to do is we're going to chop it up into segments, and we're going to apply a spectral analysis for each segment. Importantly, spectral analysis cannot take place until your specified time window is full of data. So that means for this first part, we don't have anything. And again, it's not quite full yet, so we still can't do spectral analysis. Now here we have the first time window that is full of data, so we can start doing our spectral analysis. So we do it for this one, and so on and so forth, until we have the entire time frequency representation. In this way, you're building your representation across in columns. And as you can see, power is highest when you're about roughly halfway through the signal. Okay. One more. Okay, so I'm just going to devote a few words to in terms of evoked versus induced activity. So when you have evoked activity, and this can happen for oscillations, that means that the polarity of the oscillation is the same every time the stimulus is given. Then what you can simply do is average across trials, and you'll get your feature of interest extracted. But there's also the case where across trials there's a lot of variation, and each trial the oscillation is at a different phase. So if you simply try to average, you don't get anything. It all cancels out. Rather, what we suggest is that you should actually, for each trial, compute the time frequency representation and then average across to get the feature that you're interested in. In reality, your data never looks so good on the single trial level. So what you have to do is, this is more likely what you're going to get. Somewhat of a time frequency representation at each trial, but by averaging again, you'll be able to extract the entire picture out. Okay. So when we're doing time frequency analysis, there are a couple of parameters that you want to keep in mind. And I think a good way of keeping these parameters in mind is by thinking of them in terms of the time frequency plane. And this plane is shown here. So we have the time frequency representation on the bottom. And what we've done is simply put a grid on the top. And each grid point refers to a time frequency point that you're going to estimate. So the first one is, how do you want to cut up your frequency axis? Well, you have to think about which frequencies you're interested in. And then you want to specify them simply as a vector of numbers. And so that's CFG.foy, which stands for frequencies of interest. The other thing you want to think about is, how do you want to cut up your time axes? And specify that in CFG.toy, so your time intervals of interest, or time points of interest. And now the third parameter, also very important, is your window. So how wide should each of your individual segments be for you to do the estimate? And that's specified in CFG.T_FTIMWin. Now it's important that each frequency time point that you're estimating is not an instantaneous point. It's actually an integration of the time points before and after, and also the frequencies above and below your frequency of interest. So actually what you're doing is estimating a tile, not so much an instantaneous time point. Okay. So, but then you might say, okay, well, how do I want to cut up my time frequency plane? Well, the answer is, well, it's up to you. It depends on your data. It depends what frequencies you're interested in. And in some cases, some people want to specify different time window lengths for different frequencies. And you actually do have this flexibility. You could say for every individual frequency, I want a unique time window. And that means you would have a different frequency resolution for each frequency. That's definitely possible, but you might not want to overdo it because then it makes it really difficult to compare across frequencies. So in some cases, the other extreme is say, okay, I'm going to use the same time window for all my frequencies, so then I can compare them statistically. But you should still consider and pick what you think is important for the question that you want to ask. But one small note here is that at the beginning of the lecture we said your time window determines your frequency resolution, because it's 1 divided by time tells you which frequencies you can estimate. But then we also said that if you use multi-tapering, what you can do is smooth your estimates. So if you had a 0.2 second time window, that means you can estimate with a frequency resolution of 5 Hertz. But if you apply smoothing, what you're essentially doing with a 2 Hertz smoothing, that means you could estimate from 3 to 7 Hertz. So there's some flexibility in being able to try and decouple your frequency resolution from your time window. Okay. Now, another thing to keep in mind when you're, bless you again, doing your time frequency analysis is that you have to be aware of the time frequency trade-off. So here we have a signal, and it's got a very strong frequency at 60 Hertz. And if you use a very narrow time window to estimate your signal, what you get is a very poor spectral resolution. From this first figure here on the bottom, you can't really tell at what frequency your signal is actually at. It's just too wide, and there's no way to tell. And if you extend this time window, then you start narrowing your frequencies, and you get a better and better and better estimate of roughly what frequency your signal is at. Of course, you have the case that you've actually made your time window too long, so now you have a really poor spectral resolution, so then you can't really tell where in time the effect is happening. So just be aware of this trade-off when you're setting your time and frequency parameters. Okay, so to recap, we've talked about now what time frequency analysis is, and it's basically taking your signal, chopping it up into segments, and applying a spectral analysis for each segment. We also talked a little bit about invoked and induced activity, and that you should keep in mind of the time frequency resolution trade-off when you're doing a time frequency analysis. Okay, so for the last part, we're going to talk a little bit about wavelet analysis. Wavelet analysis is another popular method to calculate your time frequency representation. And it's essentially a different approach, but it can give you similar results, but not always. So wavelet analysis is basically taking a convolution of your signal with a family of wavelets which capture different frequency components in the signal. And what is convolution? Well, convolution is just a local correlation. So you have your signal in the time domain, and then you have your wavelet, and what you want to do is do a local time point by time point correlation between your signal and your wavelet. And we can take a look at this in more detail. But just so you know, if you want to use the wavelet method, what you have to do is you now have to change your method and specify wavelet instead of MTM FFT or MTM convol. Okay, so what is a wavelet? Well, a wavelet is actually comprised of two things that we've talked a lot about in this lecture. It is a taper applied to a basis function, and this is what you get. This is a wavelet. And so what you do with wavelet analysis is you want to correlate the wavelet to your signal. And what is Fourier analysis? That is trying to use linear regression using basis functions to explain your signal. So here we're going to try and do a conceptual wavelet analysis. Here we have a really funny looking signal. It's very high frequency, and then it becomes a very low frequency in the second half. We're going to take our wavelet and we're just going to convolve it all the way along. As you can see, the wavelet better fits the features of the signal in the beginning. So you have a much better fit between your wavelet and your signal in the first half, but a poor fit in the second half. When it comes to doing wavelet analysis, you have a lot less freedom in how you want to cut up your time frequency plane. Previously, we said that you could choose, with Fourier analysis, a different time window for every frequency you want to estimate. But with wavelet analysis, most of the time you only have to think about one parameter, and that's the width, and that's the number of cycles you want in your wavelet. And after that, everything is determined for you. You don't have any more freedom. And so say we want to have a wavelet of 5 cycles, then what happens is, if you have a long wavelet at low frequencies, this gives you a very poor frequency resolution. So if you have 5 cycles at 10 hertz gives you 500 milliseconds. But if, say, you want a short wavelet at high frequencies, then you have a very broad frequency resolution, but a more accurate temporal resolution. So this diagram here shows you that once you've determined the width of your wavelet, you will always cut up your time frequency plane like this. There's no other way to break it down. It's really wide on the bottom and it gets really narrow on the top. Okay, but wavelet analysis is similar to Fourier analysis, but it's computationally a lot slower. And just keeping in mind that with the time frequency plane here, you're building it up horizontally, whereas in Fourier analysis, you're building up in columns. We're just going to compare what's the difference between doing a wavelet analysis and using multi-tapers. So on the left, you specify the method MTM convol, and then you have to specify your time points, your frequency points, and also your sliding window, and how much smoothing you want. When it comes to wavelets, you also have to specify the time points and the frequency points, but then all you have to do is specify the width. There's the smoothing, the time windows. Well, you don't need to think about that. Some people prefer to use wavelets because there are less parameters to think about, and it's just overall it seems easier. But I think the strong point about being able to use tapering is that you actually have a very good control of how you want to analyze your data. And you can configure the parameters on the left to give you something similar that's on the right. Okay, so the summary, we're done. So we talked about spectral analysis today, and we're looking at how you bring your signal from the time domain into the frequency domain. We also talked about tapering and how this is useful in controlling leakage, and that you can use more than one taper, especially when you want to estimate higher frequencies. And we also talked about how spectral analysis can be extended into doing a time frequency analysis, where you do a spectral analysis for each individual time point. And we also talked a little bit about wavelets. So this brings me to the end of the lecture. And tomorrow in the morning, once you guys have had some time to relax, to go to sleep, to consolidate all this information I've just thrown in your direction, we'll start with the hands-on tomorrow. I think it's going to be at 9. And we'll spend more time going through a lot of the different concepts that we discussed today, and that you'll be able to think a bit more about specifying time windows and what frequency resolution that you would like to use for your data. Okay, thank you.